Okay, hello everyone. Let's talk about force on an electric current in a magnetic field. Now, we talk about um, electricity creating magnetic fields, right? So if you have a conductor and if there's current I in this conductor, it creates a magnetic field around it, a circular magnetic field, looks like little circles. And the particular direction we can figure it out using the right hand rule. Now here we have a conductor. Now it's connected to a battery like this, so this end also goes to the battery. Here we have a conductor. It creates its own magnetic field. Now we take this conductor and place it in an external magnetic field, means somebody else's magnetic field. So for an example, let's say we have two magnets, two big magnets like this. So this is the North Pole, so this side is the South Pole, the other end, and here's another magnet. This end is the South Pole, the other end is not shown in the picture. So you take these two magnets, so now we know that there's a uniform magnetic field inside, and the magnetic field is denoted by letter B. And we take our conductor, which carries current in it, right? It's a current carrying conductor, has its own magnetic field, and we place it in the middle of this magnetic field. So this B is for this external magnetic field created by the two giant magnets, right? Here we have the conductor, and it has its own magnetic field, so that represented by these little circles. And using right hand rule, this first right hand rule, just thumb and fingers kind of bend like this. That's 3 fingers, there's 2 more, but anyways. So when we place a current carrying conductor in an external magnetic field, these two fields, the external one and these circles in the conductor, they interact with each other and they create a force. It creates a force. And as a result, if the force is large enough, it can move this conductor in some direction. Now this is a very important principle in magnetism, electromagnetism. This is how we create motion using electricity, motion using magnetism. This is the principle behind lot of mechanical rotational devices, things like motors, right, that we use to rotate so many things, like to rotate the fan, the kitchen appliances like like an electric blender, washing machine, the dryer, they have big rotating parts. There's electric motors inside. There's electric cars nowadays becoming very popular, and the whole thing, instead of the traditional engine, what they have is a big motor. So these things rotates because of these magnetic field interactions. We will get into details later how the motor works and all that, but for the time being, when there's a current in a conductor, it has its own magnetic field. You place it in an external magnetic field, the two fields interact with each other and create a force. And that's what we're going to discuss, right? So if you go to this PowerPoint slide on the side, a magnet exerts a force on a current carrying wire. The direction of the force is given by right hand rule. Here's another right hand rule. This is little different from the previous right hand rule. The previous one, we had the thumb in the direction of the current, and we bend the fingers around the conductor. That's the previous one. Now we have another right hand rule. You can call it the second right hand rule. Okay? We will learn another name later. For the time being, let's say the other right hand rule, the second right hand rule. So if you look at this, the diagrams, you see the U-shaped magnet. Here's the U-shaped magnet, and north and south, magnetic field going like this. We place a conductor. The diagram is kind of in 3D, so the idea is the magnetic field is going from left to right. There's a conductor going through it. It's actually going into the book or going into the board, and this is the direction of the current. Current is I, this is B. It creates a force on this conductor. How do you find the direction of the force? Use the right hand rule. Look for the diagram with the first diagram with the first diagram of the right hand, right? So it looks like this. So here we have the thumb, index finger. This completely off the scale. So let me try again. Let's try with the index finger. Okay, index finger. So take your right hand, point the index finger. Don't worry about the other fingers. Point the index fingers straight outwards. Point the thumb 90 degrees to that, so kind of pointing upward. And point your middle finger 90 degrees to both these. So it's kind of in the third direction. That's too small. Something like this. And the other two fingers, you can just bend them. Seriously, a bad diagram of a human hand. Alright. So they're all in 3 directions, right? This is pointing up. This is to the side. This is more like towards you. The 3 fingers. And we use the... Now let's place this index finger in the direction of the current. And we'll place the middle finger in the direction of the magnetic field. When you do that, the third one, the thumb, points or gives you the direction of the force. So how do we do that? Now you try this yourself. Again, I will go over this in class on video or in person, so you get a better idea about this. But you give it a try. You can also Google this, the right hand rule. Just go for a YouTube video. There's plenty of videos explaining how to use the right hand. Pretty easy. So place this index finger in the direction of the current. Place the middle finger in the direction of the magnetic field, and then thumb will be automatically pointing in the direction of the force, which is in this case going to be downwards. Right? So the force, there's a force, kind of pulling force. Try to pull this conductor downwards. Okay, that's how the right hand rule works. The second diagram of the right hand, it's the same thing. It's just another way of explaining it. You stretch, extend your fingers, all of them outwards. That's the direction of the current. And then if you bend them 90 degrees, that's the direction of the magnetic field. Thumb points upwards. That's the direction of the force. So you can use that way also. You can both means the same thing. Or you can just keep 3 fingers fixed. Index current, middle finger mag field, and thumb pointing the force. If you go to the second diagram with the magnet, the one, not the top one, but the middle one, you see the current has changed the direction. Now it's coming out from the book. Previous one was going into the book. Now it's coming out. So the way you place your fingers change. And now the thumb is pointing upwards. Let's try to understand this using another diagram. Let me erase this. So here's the right hand rule. Index, finger, the other two fingers, and thumb. Okay, right hand rule. So this is I, B, F. Let's say, let's see a good diagram. Okay, let's say I have a north pole here and a south pole here. So the magnetic field pointing this way. And I'm going to take this wire, right, and place it like going into the board. So I can draw it something like this. It's going into the, we have to understand it's more like putting a cross here. Cross means going in, right? So I is going in. This is the magnetic field. Now take the thumb, take your right hand, index finger pointing this way. Sorry, not index finger, the middle finger pointing this way. Index finger is going into the board. It's more like this. And here's the other two fingers, right? This is the thumb, this is the middle finger, which is the magnetic field. Index finger going into the board, into the book. So that's the current. The other fingers, when you do that, this is a kind of a funny diagram, thumb pointing straight up. That's the force. So the force on this is up. If you feel like this is very confusing, I totally agree. I can't draw it trying, but in class, on Zoom or in person, I will show you how to do this. Or just try some YouTube videos, right? It's pretty easy. Okay, so moving on. Now, how to do the math? This whole thing is about finding the direction of the force. If current is this way and the magnetic field is with that direction, what is the direction of the force? So you use the right hand rule to find that. How do you calculate the force? How do you calculate the magnitude of the force? We use this equation, a pretty straightforward, simple equation. Force equals I L B sine theta. Force equals I is the current, the magnitude of the current, L, the length of the conductor inside the magnetic field. So this is current. Length of conductor in magnetic field. B is the magnetic field. Sine theta, this theta is the angle between the conductor and the magnetic field. So angle between magnetic field and current, or the conductor, right? The current goes through the conductor. So current and the conductor means the same thing. F equals ILB sine theta. Sometimes I write it this way. F equals BIL sine theta. Easy to remember. Bil sine theta. F is the force. So ILB sine theta. If you are in advanced maths classes, we can explain this in the vector form. It's the cross product between L and B, or between current and B. Current is not a vector, so we take the length as the vector, so because it has the direction. Either way, using this, we can find the magnitude of the force. So let's try some simple examples. But before that, let's talk about the units. Unit of B, magnetic field. The unit is the familiar word Tesla. denoted by letter T. This comes after the famous scientist Nikola Tesla. Elon Musk used the term Tesla for his car company. It's like an honor to the scientist. There's another person started a trucking company, Nikola. It's like a rival. Anyways, Tesla is the unit. Tesla is also Newton per ampere meter, but we can just call it Tesla. 1 Tesla. There's another unit for magnetic field, which is Gauss. 1 Gauss, it's a smaller unit, is 10 to the negative 4 Teslas. So most of the lab-related magnetic fields, small magnetic fields, we use Gauss because it's a smaller unit. But when it comes to large magnets, superconductors, the magnets in MRI machines, we use Tesla term. Okay? Alright. Let's see what examples we're going to discuss. Okay, before this, let's try a simple one. So let's go back to the equation. Force equals ILB sine theta. Let's say for an example, we have a magnetic field, a uniform magnetic field of, let's say, 2 Tesla. In that magnetic field, we place a conductor carrying current. Length of the conductor is, let's say, 3 meters. It's carrying a current of, let's say, 4 amperes. And this conductor is 90 degrees to the magnetic field. So theta is 90 degrees. How do we draw all this thing in a simple diagram? So here's the magnetic field. So let's draw the magnetic field like this. Here's the B field. There's a conductor. The conductor can have any length. What we need is the length of that conductor within the magnetic field. So here's the conductor. It's perpendicular. It's 90 degrees. This is the direction of the current. You measure it from B to I, and it's 90 degrees. Carrying a current of 4 amperes. 2 Tesla. This length, this is the length we are talking about, within the magnetic field. If this is not perpendicular, then we have to use sine theta. Here also we use sine theta. So we have all the information. L is 3 meters. So what's the force? F equals ILB sine theta. 4 times, 3 times, 2 times sine 90. 24. Sine 90 is 1. So 24 newtons. The force acting on the conductor due to this magnetic field and current is 24 newtons. Okay, let me take a new page. Let's try another example. What's the significance of this theta? Equals ILB sine theta. Now you saw that we have the magnetic field. We placed the conductor like this, creating 90 degrees, and we found out what the force is. What if you have the magnetic field? What if you place the conductor parallel to that? Here's the conductor. Here's the direction of the current. If these things are parallel, magnetic field and the direction of the current, if they are parallel, theta becomes 0. Sine theta becomes 0. Force becomes BIL sine theta, or ILB sine theta is 0. Whole thing becomes 0. So if the current goes parallel to the magnetic field or anti-parallel 180, force becomes zero, right? So then that tells us that if we rotate this conductor, right, this wire, you have the max when it is 90 degrees. You have the minimum when it is 0 degrees, when it is parallel. You will have something in between if the conductor has some angle theta between that and the magnetic field. And it's the sine of the theta. Okay? Okay. Alright, let's try this example. A wire carrying a 30 ampere current has a length of 12 centimeters between the pole faces of a magnet, an angle 60 degrees as shown. So it's like this diagram I have here. B is the magnetic field is approximately uniform at 0.9 Tesla. Theta is 60. Length L is 12 centimeters. And the current it carries, I, is 30 amps. Asking what's the force? F equals ILB sine theta, 30 times 12 centimeters, 0.12, magnetic field 0.9, sine 60. So take the calculator, do the math. Let's see what we have. 30 times 0.12 times 0.9 times sine 60 is 2.8. The force is 2.8 newtons. Now you can give a try and try to figure out what's the direction of the force. So again, middle finger in the direction of the well, I'll let you guys figure it out. It's a little difficult. You have to bend your hand, be careful, don't break your wrist. But if you can correctly place the middle finger in the direction of magnetic field and index in the direction of current and keep them perpendicular, you will figure out what direction is the force is. Okay, let's move on. Okay, so before we move on, I have two more questions for you. What are the maximum and minimum forces we can create using this setup? Minimum is pretty simple. Place the magnetic field, place the conductor in the same direction. This is the B field. This is the conductor. Place it parallel to that. Force becomes what? 0, right? Because theta is 0, sine theta becomes 0. What's the max force you can create using this setup? Place it perpendicular. Place the wire like this. So that will be F equals BIL sine theta. This whole thing is 1. Sine 90 is 1, so it's going to be magnetic field 0.9, current is 30 times 0.12, and whatever that magnitude is. That's the max. Okay, so try this. Okay, we tried this question. Try the next question. Try this. Oh, kind of made a mess. Hold on. Anyways, it's so a rectangular loop of wire hangs vertically as shown. Magnetic field B. Yeah, that's what it is. There should be a letter B here. Alright. B is directed horizontally perpendicular to the wire. So you see these little blue circles with the dot inside telling there's a uniform magnetic field coming out from the board towards you, coming out from the computer screen towards you. And there's a loop of wire in it. You see the current is flowing in this loop in a counterclockwise direction. So the other information given, the length and all that. So the question is, what is the magnitude of the magnetic field? So give it a try. It's a good question. Try it. I'm not going to do it. It's for you to try. I will give you the answer. B. Answer for this magnetic field is 1.42 Tesla. Okay, so give it a try and see whether you can get this answer. Okay, let's move on. So the next topic, next one, force on an electric charge moving in a magnetic field. This is also a very interesting topic and has a lot of applications. In science experiments, in biological experiments, charged particles are moving inside the human body in biological systems, and these charged particles experience forces due to magnetic field, Earth's magnetic field for an example. How do we find those? So we know that a current carrying wire, there's current in this wire, that means electrons are moving, and you place it in an external magnetic field. These electrons they feel a force. The whole wire feel a force because of these charged particles inside are feeling a force, right? So in this case, the wire is like a medium where this charge can move through. It's a path. It's like a guiding medium. If we can have a beam of charged particles, let's say a bunch of electrons, we can shoot them in one direction, or a bunch of protons, shoot them in one direction. That is like a current, right? Charged particles moving. That's a current. So you don't really have to have a conductor. You can just get a charged particle, accelerate it, shoot it in some direction. That can be considered as a current. Now, if a charged particle, as long as let's say a proton, as long as it's moving without any magnetic field around it, well, it creates its own magnetic field, but as long as it's not subject to an external field, it goes in the same direction. There's nothing to slow it down or change the direction. But if you subject it to an external field, there is force on it. We talk about F equals BIL sine theta. This is for a conductor with some length. Same way for a charged particle, we have F equals QVB, or we can say QV cross B. So how do you understand this equation? Okay, how do you understand this? Now let's take a look at this PowerPoint diagram. Here you see that a magnetic field, north and south. So here's north, here's south. So here's the magnetic field. Let's say we have a positive charge. In the diagram it's denoted by plus Q, right? But let's say a proton. So it's coming in this direction. So the proton comes in. You can use the right hand. It's a positive charge. So in this right hand rule, direction of the current is same for the direction of the proton. It's a positive charge. So the direction of the proton is the direction of the current. It's the opposite if you have an electron. This is a negative charge. That means if the electron is moving to the right, the finger should be pointing to the left. If the electron is moving down, index finger should be pointing upwards. Right? So the current is considered opposite of the direction of the electron. But for a proton, if proton or the positive charge going this way, index finger also pointing the same direction. So you place the index finger in the direction of the current, you place the middle finger in the direction of the magnetic field, the thumb will be pointing up. So a positive charge gonna deflect upwards. It's coming in, it's gonna deflect up. If it is a negative charge like an electron, you have to place the current in the opposite direction, so that gives the thumb in the downward direction. It comes in, deflects downwards. Again, I will go over this in class, so you will be able to get a better idea. But again, YouTube should have a lot of simple videos explaining this. Now, how do we find the magnitude of force? F equals Q V D, that is sine theta also. This is the charge. So if it is a proton, we know that this is going to be 1.6 10 to the negative 19 coulombs. This is the speed, velocity, how fast it's coming in. Magnetic field. The angle between the velocity and the magnetic field. Angle. So again, let's say we have a magnetic field like this, and you shoot a proton directly across it, making 90 degrees, theta becomes 90 degrees. Here's the magnetic field, you shoot the proton parallel to that. Here's the proton, here's the magnetic field, theta is 0. You can shoot it at some angle, like this, here comes your theta. Alright, so let's try a simple example. Okay, so let's say we have a proton moving at a speed of let's say 3 times 10 to the 6, pretty fast, meters per second. This proton enters a magnetic field perpendicular to the magnetic field, and the strength of the magnetic field is, let's say, 1.5 Tesla. Alright, so what's the force acting on this proton? Which way it's going to deflect? Now, let's say the proton is moving perpendicular to the magnetic field. I am going to draw the magnetic field, and you can draw the magnetic field any direction you like. It can be like this, it can be like this. I'm going to say we have a magnetic field going into the board, right? Going into the screen. So I'm going to draw it like this, crosses. It's like going into the thing, into the screen. So here's the magnetic field. Proton is going perpendicular to that. So proton can't be going into the board or out of the board. It should be to the side or to the up, to north, south, something like that. So let's say proton is coming from the left. Here comes the proton with the velocity v. Now, what's the force acting on it? Which way it's going to deflect? We're going to use the right hand. So again, take your right hand, place the index finger in the direction of this proton, right? So to the right. So here's your right hand, here's the index finger going right. Magnetic field going into the board, place the middle finger on these crosses into the book. So it's like, how to go there? It's kind of going in. And so this is going in, okay? This is the middle finger, this is B field, this is index, this is current. Here's the other two fingers. Now this is your right hand, but what you see here is not the palm, the back side of your right hand, okay? And then when you do that, your middle finger, your thumb actually going up. So that means the force on this proton is pointing. Once it enters, force will be upward, so eventually it's going to deflect like this. And what's the magnitude? Q V B sin theta. Charge of the proton 1.6 10 to the negative 19. Velocity of it 3 times 10 to the 6. Magnetic field 1.5 sin theta. We say in the problem proton and magnetic field are perpendicular, so sin 90. So what do we have? (7.2 times 10 to the negative 13 newtons). Comparatively small force, but enough to curve this proton upwards. Okay, we will go over a lot more examples. Let me see whether there's any conceptual stuff we can quickly take a look at. Okay, I'll let you read this and have an idea. Here's another problem. You might want to pause the video and read this because I'm quickly going over them. So you might have heard that I did some research projects a few years back on magnetory reception, how certain insects sense Earth's magnetic field for navigation and stuff. So this is actually one a kind of an application to that. Certain insects can sense these changes. They can sense these forces. As of now, there's no evidence that we can, but certain insects like certain birds, butterflies, they can. If a charged particle is moving perpendicular to a uniform magnetic field, path will be a circle because it keeps changing the direction at every point and ends up. If the magnetic field is broad enough, you can bring it to a circle. And this is how some particle accelerators work. They bring the charged particle into a circular path, and then while circulating in it, you can accelerate it using some techniques. Okay, a few more examples. So describe its path quantitatively means it comes into a circle. What is the radius of the circle? Now here's an interesting question. You know that when there's a force, it pushes the charged particle into a circular path. But how big is this circle? That depends on all these factors. How much force it's getting, what's the mass of this thing, how fast it's moving. Think about centripetal force equations. You should be able to figure out the radius. And a magnetic field is used to stop a single charged particle, as an electric field can. something like this. Remember, electric fields, so positive and negative plates creates electric field like this. So if you shoot a proton, let's say take a proton here and you shoot it this way against the field, we know that the proton is being pulled to the negative side, it's being pushed away by the positive side. So if you shoot it in the opposite direction, if the field is strong enough, this will slow down and eventually will turn around. It will come to a full stop here and before turning around. Can we do the same thing with magnetic fields? Something to think about. Okay. A summary of all this. The first right hand rule to figure out the direction of the magnetic field around a conductor. The second right hand rule, we use this format here. The second right hand rule is when you place a current carrying conductor in an external magnetic field, what happens? That's the second right hand rule. So if it is not really perpendicular, if you shoot it with a little bit of an angle, you can actually bring it to a spiral like this, helical path. And there are some interesting questions to figure out the distance between these little circular loops. Okay. Alright, I think that's enough for this this video. We'll discuss more in the coming videos. Alright, thanks.